Okay, welcome back, guys. We'll be looking at section 2.3 today, and I might be able to get it in one video. I don't know, we'll see. Okay, but what we're going to be focusing on is the determining the domain and range of a function. Okay, so we spent some time last class talking about identifying whether a relation or a relationship between x and y was actually that of a function, whether y was a function of x. And we did discuss what the domain and the range of a function are. We said that the domain is basically the set of all the inputs, and that the range is the set of all the outputs. And we were using that juicer analysis or analogy, in which, in that particular example or analogy, the domain would be the set of all the different fruits that can be juiced, and then the range or the outputs would be all the different types of juices. Okay, grape juice, apple juice, orange juice, etc. And so the same thing works with a mathematical or an algebraic function. All the values for x that work or that can be input into the function such that you get an output, they make up the domain of the function. It's typically a set of values, okay? And that set can be infinite as well, and typically is. And then the range is basically the set of all the outputs. What are all the numbers that the function outputs or produces, okay? And we're going to start by looking at a pretty simple function. And we actually have it graphed right here. This is a very simple function, guys, because for one thing, it's not what we refer to as a continuous function, meaning, you know, if you were to graph it, you wouldn't be picking up your writing utensil. It would just be a continuous curve or a continuous line. Okay, this one is actually made up of 5 points. And we're not really going to be seeing many functions like this. This function only consists of 5 points. Most of the functions that we see are going to consist of infinitely many points. That's where we get those smooth curves or those lines. Okay. But what we want to also get some practice with is determining the value of a function strictly by just looking at its graph. Now, we looked at evaluating the function when we knew what the function was. So, for example, if I explicitly know what the function is or have a formula for the function, and I want to find f of 1, well, x is 1, so I just take 1 and I plug it into x in the function. Okay, but if the function's already graphed and we don't have the function explicitly expressed, then we can't just plug 1 into it. Okay, we actually have to look at the graph, and that's what we're going to do with this first example. This first example, we want to find f of 1. Okay, or in other words, whenever x is 1, we want to figure out what y is. Okay, because y represents the function value. So what you're going to do is you're going to look at the graph of the function, and you're going to find the point that corresponds to 1, such that x is 1. And there's only one point, and it's right here. Okay, this point has an x coordinate of 1, and to evaluate the function, you look and see what that corresponding y coordinate is. And in this case, it just coincidentally also happens to be 1. Okay, and so because of that, we can say that the value of the function whenever x is 1 is also 1. Okay, so it's just a coincidence that they happen to be the same value, both the input and the output. So the input here would be 1, and the output is also 1. Now, the second thing we want to do is identify the domain of this function? Well, because this function consists of only 5 points, the domain is just going to consist of 5 values. And it'll be those x coordinates from these 5 points. Okay? Remember, think about your domain as being all the values for x, and your range as being all the values of y. So the x coordinates of these 5 points are going to be -3. This one has an x coordinate of -1, 1. The x coordinate of this point is 3, and then 5. Okay, and so the way I list those is I can do it this way. The domain is this set. Typically, to denote a set, guys, you can use these curly braces. It's literally just the set of those 5 numbers. -3, comma, -1, and we're just listing them here because there's just 5 of them. Okay? If there were infinitely many numbers, we wouldn't list them. There would be another notation that we would use. Because it would be impossible to list an infinite number of numbers. Okay, let's see, 3 and then 5. Okay, so this set of 5 numbers right here is the domain. It's basically the inputs to whatever this function is. Now what we want to do in part C, it says find all x values such that f of x is equal to 2. So here we're kind of going in reverse from what we did in part A. So they're telling us that the value of the function is 2. Well, the value of the function is the same as the y-coordinate. So in other words, we're trying to find a point such that its y-coordinate is 2, and then figure out what the value of x is. Okay, because it says here to find the x values, and it could be value or values such that the y is 2, in other words. Okay, so you're going to find the point or points such that the y-coordinate is 2. So here's 2 on the y-axis, and I only see this one point right here that corresponds to that value of y. And so I look down here on the x-axis, and I can see that it corresponds to 3. So to answer this one, x has to be 3. Or in other words, for you to get an output of 2, the input has to be 3 for this function. Alright, and then finally part D says we want to identify the range of this function. Well, again, the range is just the set of the output values. Okay. Well, again, because there's only 5 points, there's only going to be 5 values in the range. And they're going to correspond to the y-coordinates of all these points. So the y-coordinate of this point is -1. This point has a y-coordinate of 0, and then 1, and then 2, and then 3. Okay, so I can list them again. The range is going to be this set of numbers: -1, 0, 1, 2, and 3. Okay, so like I said, this is a very simplistic function in that its domain only consists of 5 numbers and its range only consists of 5 numbers. Typically the domain and the range for functions is actually infinite, and lots of times, guys, the domain from a lot of the functions that we're going to see is going to be all real numbers. And think about what we've done previously when we were working with functions. When we were graphing them, we could pick any value of x that we wanted, as long as it was a real number, and we could plug that in and we would always get an output. Now that didn't always work graphing them, because lots of times that actual ordered pair would be outside of our viewing window. So it wouldn't make sense to pick a value of x that was, you know, like 10,000 or something like that. Alright, well, let's move on to one a little bit more I guess, I don't know if I would say complicated, but actually before we do that, let's look at, so this last example, I told you this is not a continuous function, okay? So let's look at an example of a function that is continuous. This one right here. So this is a continuous function. However, this function doesn't have arrows on the ends of it, so that just means that it doesn't go off in both directions or in opposite directions, okay? This function starts at this point and it stops at this point. Well, the domain would be the value of all the x's of all these points, okay? In other words, it would consist of this region on the x-axis, this region of numbers on the x-axis that correspond to this point, which starts at -5 and then stops at this point, and that has an x-coordinate of 3. And so we can write the domain or express the domain like this. We can say it's all values of x such that x is nestled between -5 and 3. Okay. Another way to express that is in something called interval notation. And interval notation works like this. You list the starting number, the lowest number that's in the domain, which is -5, and then you list the highest number that's in the domain, which is 3. And then you don't worry about listing all the numbers in between, okay? You're basically saying right here that the domain is all the numbers between -5 and 3, and then these brackets intimate that -5 and 3 are included in the domain or in that set. Okay. They're included because these 2 points on the ends, they're closed, meaning these are points. These make up the function. Okay. What I'm really trying to point out to you guys, though, is that the domain consists of this interval right here, because that's where this function exists with respect to the x-axis. Now, similarly, if you look over here to the right, the range would just be the set of all the y-coordinates of all the points. Okay, so starting at this lowest point, it has a y-coordinate that starts right here at -1, and then this highest point has a y-coordinate of 4. And then all these other points on this function have y-coordinates somewhere between -1 and 4. Okay, and so in interval notation you would list it like this. It goes from -1 to 4. Okay, and again we are including those 2 end numbers because those 2 endpoints are included. They're part of this function. Now, if you're expressing this in what's called set builder notation is where you write it like it's a set, so you use these curly braces, but you say all values of y such that, and then you list the characteristics that y would have, such that y is between -1 and 4. Okay, the way I have it, or the way they have it listed right here. And notice I'm using y because we're referring to the range. If I was talking about the domain, I would have it listed like this. All values of x such that x is between these 2 numbers. Okay. Alright, so when we have these infinite sets, there's 2 ways that we can use to describe that infinite set of numbers. This way is called set builder notation, and well, the book tends to prefer set builder notation. But most math books that I worked with when I was in college, they prefer to use this notation, which is called interval notation. Interval notation is much cleaner, in my opinion. Okay. Alright, but anyway, we'll get some more practice here with this example 2. Okay, so example 2 here. It says for the function that's graphed below, we want to find the value of the function when x is 1. We want to find its domain. We want to figure out what value or value of x's give us a function value of 3, and then we want to identify the range again. Okay, so this one is like example 1. The only difference is example 1 was a very simple function in that it consisted of only 5 points. This function here, guys, you recall, this is actually the graph of an absolute value function. Remember, this is going off in both, actually used, I can't remember if I think I showed you guys this, yeah. I actually used Desmos to graph this one. This is going in both directions, so this is an absolute value function. You can see that it's centered right here at -3 on the x-axis. Okay. They don't have the function expressly written. All we see is the graph of the function. But we can, nonetheless, still find the value of the function when x is 1. And that's what we're going to do. Okay, so when x is 1, we need to figure out what y is. So what you're doing is you're looking at your graph and you're trying to find the point on this absolute value function that has an x-coordinate of 1. Well, 1 on the x-axis is right here, so the point on the function has an x-coordinate of 1 will be right here. Okay, and so what's the value of the function when x is 1? Well, it's right here, it's 4. Okay, or in other words, whenever the input is 1, the output is 4. Alright, now what about the domain? Okay, well, because this is a continuous function, the domain for this function is going to be an infinite set. Okay, it's the set of all the x-coordinates that make up this function. Okay, well, this function is made up of infinitely many points, one stacked right after the other. Okay, and so what happens here, guys, when you have a continuous function that's going off in both directions, both toward negative infinity on the x-axis and also positive infinity, then the domain is going to be the set of all real numbers. It can be written a couple ways. It can be expressed in interval notation by saying the domain goes from negative infinity to positive infinity, or it can be expressed in set builder notation by saying the domain is the set of all values of x such that, and then you can write in here, x is a real number. And this is the way the book does it. Okay, and this is what you're going to see in your homework. All values of x such that x is a real number. This just means that the domain of this function is the entire x-axis. This absolute value function, if we actually saw what it was explicitly, you could plug any number in for x, and it'll always give you another number for y. Alright, what about part C? Part C says find all x values such that f of x is 3. So again, we're going in reverse. We're going to find the point or points that have y coordinates of 3 and see what those corresponding x coordinates are. Okay. Alright, well, I'm looking at my graph right here. Here's 3 on the y-axis. And there's actually a couple points. It'll be this point right here and then this point over here. Okay. So I'm going to highlight those. I'm going to use this color. Okay, so there's actually 2 points. Both of these points have function values or y-coordinates of 3. Okay, so to answer my question, the x-coordinate that corresponds to both of these, this one corresponds to -6, and then this one has an x-coordinate of 0. Okay, so when f of x is 3, then x has to either be equal to -6 or 0. Okay, and in the homework, guys, you have to list them one after the other with a comma separating them. Now, don't list it as an ordered pair, because it's not. We're just simply listing the x-coordinates of these 2 points. Okay, because these are the only 2 points that have y values or function values of 3. Alright, now lastly, for part D, we want to identify the range of this function. Well, I'm looking at this function and I can see that it's basically, it's sitting on top of the x-axis. And so consequently, all the points that make up this function are going to have y-coordinates that are either 0 or greater, positive in other words. Okay, so the range is going to be basically all the positive numbers with 0. Okay, so if you wanted to express it in interval notation, you could write it like this: from 0 to positive infinity. Okay, this just shows, and by the way, this center point is included. Okay, so 0 is included in the range. That's why I used a bracket right there. And then every other number greater than 0 is included. So from 0 to positive infinity. Okay, positive infinity would be up here. Which, by the way, guys, infinity is not a number. Okay, but we can sort of treat it like it's 1. We can sort of treat it like it's the biggest positive number. And similarly, we can treat negative infinity like it's the smallest positive or smallest negative real number. Okay, even though they're really just concepts. Now, I want to also express the range in set builder notation. Okay, so I would do that by saying the range is all values of y such that. So how do I show that y is either 0 or a positive number? Well, I express it as an inequality. I say y has to be greater than or equal to 0. Okay. Actually, the book or the homework does it like this, writes it out like this. I think it'll say that y, well, I can't remember if it goes ahead and says y is a real number and then it says y is greater than or equal to 0. I'm just going to put y is greater than or equal to 0. Okay. This just means that y is a real number, a positive real number, or 0. That's all that means. Now, what would the range be if this were turned upside down? If it were turned upside down, then the range would be just the opposite. The range would be all the negative numbers up to 0. Okay? So y would be less than or equal to 0 in that case. Alright, we've got a couple homework problems similar to these two. Okay. And guys, I looked around on YouTube for kind of a fun video that simplified some of these concepts, and I couldn't really find one. So anyway, Alright, I think actually what we'll do is we'll go ahead and stop this one because I'm already 25 minutes in, and then we'll use part 2 to finish this one up. Okay. What we'll be doing is finding the domain whenever the function is not graphed. Whenever we're just looking at the explicit form of the function, how do we find the domain in that case? Well, we could graph it and then use the strategy that we used from up here to try to figure out the domain. But there's really a better way to do it, a more mathematical way to think about it. Alright, so I'll stop for now.